You know already the authors and co-authors and our institute, and you have seen already our outline, and now I must show that still two items remain, and these two items may be called other nano architectures. First, these investigations were performed in order to address extremely important practical question. I mentioned earlier that we started from general idea, but how to implement it? And in order to model what happens to vortices and vortex chains and phase slips in structures of realistic sizes, we spent some time and effort to develop a platform which performs really three-dimensional calculations. The same equations, but in 3D. And here two key results. Look now at a model C-shaped structure. So it's not a tube now. It's a model of the upper part of the tube. And this is the model of the lower part of the tube. But here we have a link which was missing in the previous case and in my reply to your question. That link did not exist and it does not exist in the tube or in the spiral. Geometry is the same, but if the plate is 200 nanometers thick, and if the distance between two plates is about 60, 70 nanometers, these two sets of vortices which develop in both plates practically do not feel each other. This size is enough in order to prevent inductive interaction between them. And if the Magnus force is present, then the upper set starts to move, for example, in this direction, the lower in this direction, and I think this is a situation which can well be modeled by a two-dimensional structure. It's three-dimensional, but the vortices do not feel each other. Now, next step. If you make these two plates larger, okay, and the distance between them, here it is 30 nanometers all over, so they are closer to each other. You see what happens to vortices? We have just heard from Professor Rudnev about some deformation of vortex lines, but here we see a deformation. Look, this is a precursive vortex. If it starts in the upper part, it seeks for continuation of its core in the lower part. But then what about motion? Now it's already interplay between the spinning force between vortex in the upper half and in the lower half, and Magnus force. Magnus force is controlled by magnetic field and the velocity of vortices. And if Magnus force prevails, then the vortices nevertheless move, but they move rather slowly because they are peeled. It's the same phenomenon like you were telling us. If the vortices are peeled, in this case by each other, they move slowly. But if the pinning force is stronger, they do not move, and we have nothing mobile but an precursive vortex with some defect inside of it because there is no superconducting material in the center. So cannot go outside of a superconductor. It belongs to a superconductor. It's a part of superconducting state. But the change of magnetic field in this case, due to a renormalization of it, is somewhere 20%. Correspondingly, the induced voltage also changes by 20%. This already should be taken into account if we arrive at such structures. But these are very, very small distances. In our tubes, they are never such small. So 2D approximation, fortunately, works very good. Next. I attracted your attention to helical coils. Imagine that you perform rolling up and you get an open nanotube. But if you change the direction of rolling, it's a matter of technology. And if the rolling occurs at an angle with respect to the axis of rolling, you will get a helical structure like this, for example. And here typical sizes are shown. They are micrometers, but the thickness of this niobium film is 50 nanometers. And if you ask a rigorous definition, it is nanostructured microhelix. But we will call it nanohelix. Okay. Again, magnetic field is strongly inhomogeneous, as I showed you. Its normal component is shown here. Therefore, the vortices, if they occur only in the upper half winding and lower half winding. And here already some new phenomena may occur. Incommensurability. If you have 4 half windings and 9 vortices, where should sit the 9th vortex? It has different places to sit. It is incompatible, it's incommensurable. And it can sit either here or here, it can be in different places, and this will certainly be of great importance for transport, because the states, quantum states in this macroscopic quantum phenomenon are degenerate due to this positioning of additional vortices. The experiment, which I will briefly discuss now, was performed on a real nanohelix, which was obtained by focused ion beam deposition of tungsten carbide. And I think the numbers are clear enough to show that the diameter of this nanohelix is 100 nanometers. And the line is about 30 nanometers. So it's completely nanohelix. And these experiments were performed in Zaragoza and Valencia. And the more interesting observation, which was not on all available nanohelices, but on some of them, is related to the occurrence of such steps in the resistance as a function of current. At different temperatures, different magnetic fields. Here is 2 Tesla, here is 1 Tesla. And our interpretation of this observation is related to the theory which we have got acquainted. If if the transport current is small enough, like here, in half windings, we might have a few vortices, you see, but vortices produce or induce voltage rather small. And practically, we are very close to this superconducting regime. It's maybe some deviations of it, but it's practically superconducting regime. But then, at a certain value of this transport current, in some of the half windings, I emphasize some, not everywhere, phase slips occur. Those which we were looking at in nanotubes. So there are phase slips. Phase slips are related to suppression of superconductivity. Therefore, these blue regions are practically normal conducting. As soon as they are normal conducting, they contribute to the measured voltage and correspondingly to the measured resistance. And this corresponds to this regime number 3. It's already some resistance, 1 kilo ohm. Let's increase this current. And at a certain another value, higher value, the phase slip appears also in 2 other half windings, because the distribution of the water parameter is not uniform along the nanotube. They do not appear everywhere in a homogeneous mode. And here we have already more contributions to the resistance, and we have regime number 2. And current, which is already critical current, all nano helix is filled in with phase slips, but this is nothing else but normal stage. We have the end of the resistive transition to the normal stage. And our calculations, which were related to the experimental geometry and experimental data, these materials are not yet so nicely characterized as niobium, and their nanostructuring changes their materials parameters. Okay, we know this also for niobium, but for this material, everything should have been checked from the very beginning experimentally. We got very nice correspondence even in what concerns the height of the steps. And this is a consequence of phase slips, not in a tube, but in a nanohelix. Topology of the screening currents is similar. No good. This is explanation of what I have just told you. Maybe still a couple of remarks at the end. But why in some cases we observed smooth transition from superconducting regime to normal state. In order to bring some light to this, look at calculations made for different nanospirals with different number of windings. So this is 1, 2, 3, and 4. The phenomenon remains the same. The phase slips may occur only in the half windings, either in the top or in the bottom, where the magnetic field normal to the nanohelix is maximal. But there are many more half windings, you see, and the contribution to the measured resistance depends not only on the fact that there are effects, but also on the size of this area where we have. And if these half windings, which do contribute to the resistance, are becoming rather narrow, then their contributions may be stepwise, are rather small, and you may in fact see a staircase with many steps, but due to some experimental uncertainties which are always present, we perceive such a staircase as practically continuous transition. So at least such a possibility remains, and I think I write the very last slides, which also represents new work of this year. So it's a tungsten carbide nanowire, which now is put in an electric ray. Light, superconductor is electric. Expel electric field, but this is nanowire. The macroscopic idea is different light nanowire. So this there is a voltage and experimental measure. There is resistance, the department of current through the wire at different gate voltages. This critical current is obtained from this set of standard. Occurs strongly dependent on the gate voltage. And the explanation exists now is not only our explanation, but it is in order to perform modeling within time dependent system locality. Because the electric field needs this busy or superconducting scale is wire into a channel which is narrower than the geometrical base of the wire. And if this process continues, then finally this channel becomes narrower and narrower, and the second value of the gate voltage. There is no more superconducting material in the nanowire. We have already normal scale. Therefore, in this case, electrical current does not apply. And these are dependencies of the critical current and the gate voltage for different temperatures, which are for every temperature in a reasonable range. So simply to help with not only this magnetic field, but also this electric field, we get these very novel and unusual properties of superconductors and nanotubes.
3 minutes.
I already finished. I promised you to be on time. I would like here to say that signatures of vortices and phase slips have been experimentally identified and supported by our numerical simulations, but these works are also ongoing, and it's really terra incognita. We know that the properties of light superconductors constitute the main contents of such a really great conference. But if you still add confinement, you add some geometrical and topological features, which, in my opinion, leave us grounds for optimism. At this point, I would like to thank you for your attention.
Thank you for the presentation and for the optimistic notes in the very end. So my question actually relates to one of the very last slides with this gate control superconducting state and narrow nanowire between the gate electrodes. Did you consider to apply not a constant voltage, but a high frequency alternating voltage to see the microwave frequency modulated superconducting state in this wire?
Yes, I think this is very interesting possibility. This was the first penetration in these materials, and I do appreciate your suggestion to make also here an alternating component to the current.
Because there are at least two aspects. That the microwave field will be inducing transitions between the vortex chain to phase slip regime with different frequencies of be it Josephson generation or time of flight across the wire, or the stimulation of superconductivity itself.
Yeah. Thank you.
Thank you very much. Is there another question? Yes, there is.
What is the absolute value of critical current, for example, for Kelvin in this case?
I do not remember.
Approximately.
Sorry, I can show you it after the talk, but okay, here the typical currents which are represented here, unfortunately you cannot see it because they are small. They are of the order of 1 to 2 microampere.
Okay, thank you.
Thank you. Another question, please. Yes, could you take microphone over there?
I just didn't understand, so I would like a clarification. The normal component of the field you showed that is variable, so there are areas which are, let's say, with vortices and areas which don't have. Is this a self field or it's imposed from outside? Sorry, I don't understand this aspect.
You mean magnetic field?
Magnetic field, orthogonal to the
Yes,
cylinder.
yes. It's a product of geometry. I will now return to the slide fast. Oh, this is true. This is. Let's make a thought experiment. This is my cube or part of spiral, one winding. This is my magnetic field. And we apply it as said orthogonal to the axis. The magnetic field is uniform. It's very easy to do correctly. For vortices, we need a normal to the surface component of the magnetic field. And here on the top, it's just maximal value. It's the same value as the applied field. In the bottom part, it's the same maximal by modulus value equal to the applied field. But if you go now to the side of this cube, the magnetic field is tangential. Tangential field is maximal, but we do not need tangential field. Vortices do not feel tangential field. They need normal field, and we do not have normal field. And this is just what is shown in the first panel.